So we're going to jump into a new topic, which is about utilizing something called matrices. So the idea behind this is we want to take our traditional systems of equations that you probably remember having to go through substitution and elimination to solve for, but we're going to look at a different method. And this kind of leans into a branch of mathematics called linear algebra. So if you have to go on to this class, you'll learn more in depth about these, and you'll learn about different properties and things like that. All we're going to be focusing on is looking at solutions to linear equations using matrices. So something that might be really helpful for you is to actually go back through and refresh on how to solve a system using elimination and substitution. I'm going to do just a simple example of two equations with two unknowns, but you can go back and refresh on three equations, three unknowns, and all the different methods for that, okay? So we're going to try this example. We are going to solve this equation. So if you want to do substitution, you would have to solve for one of the variables x or y in one equation. You then would plug it into the other. However, with this, if I were to try to solve for one variable, it would not be pretty, because if I solve for x in the first equation, I got to divide by 3. And that would not be nice to have to work with fractions. Same thing if I tried to solve for y, I'd have to divide by 6, and that would not be pretty either. And likewise, in the second equation, if I want to solve for either variable, I have to divide by a 5 or a 4, and that's going to involve fractions. So I think elimination is a much easier way to go about this problem. So remember, our goal is we want to add these equations together so one variable eliminates. So you want the constant out front to be exactly the same, but opposite signs. So looking at the y coordinate, I like that a little bit better because one is already positive and one is negative. I just want to get it so that the number out front is the same. They're already opposite signs though. So if you think about 6 and 4, well, you can turn both of them into 12. So I'm going to take this first equation and I'm going to times it by 2. And then I'm going to take the second equation and times it by 3. So I'm going to do the same thing to both sides. So the first equation, when I times it by 2, gives me 6x minus 12y equals 4. When I take the second equation and times it by 3, that gives me 15x plus 12y equals 3. And now these two have exactly the same y value, but one is positive and one is negative. So we can go ahead and add these two equations together, and that's going to make that y eliminate. Okay? So then I just add the like components. So 6x plus 15x gives me 21x on the left, and then 4 plus 3 gives me 7. So going through and solving for x, we have to divide by 21. So our x is equal to 7 over 21, but both of those are divisible by 7. So that reduces to 1/3. So the x value that solves this system is 1/3. Then to figure out y, I just need to plug x back into either one of these equations. I'm going to go ahead and just pick the first one. So we need 3x minus 6y to equal 2. So x I know is 1/3, so I plug in 1/3. And thankfully 3 times 1/3 gives me 1. So we get 1 minus 6y equals 2. Then going through and solving for y, we have to move the 1 to the other side. So that gives us negative 6y is positive 1. And then dividing by negative 6 tells us our y coordinate has to be negative 1/6. Okay. So this is that point of intersection for these two different lines. If you had 3 equations and 3 unknowns, you just have to reduce it to a system of 2 equations and 2 unknowns. But what we want to do is, instead of utilizing this process of elimination or substitution, we're going to use a matrix to solve these systems. So we're going to just talk about first what matrices are. We're going to talk about something called row operations, And then we're going to see how we can use a matrix to instead solve a system of equations. So an M by N matrix is a rectangular array of numbers with M rows and N columns. So the first number is always indicating how many rows there are. The second number is indicating the number of columns. So to give you an example of this, say we look at a 2 by 3 matrix. That means there's 2 rows and 3 columns. So the nice thing about matrices is they're just going to be able to keep track of the numbers instead of the variables. The position is actually going to be what tells us the variable. So maybe I have the numbers 1, 2, 3, 4, 5, 6. Okay. So again, 2 rows and 3 columns. Right? If I have a 4 by 1 matrix, that tells me there are 4 rows and a single column. So maybe I have the numbers, just to use 1, 2, 3, and 4, okay? So what happens is when we have a system of equations, we can always turn it into a matrix, and it's called an augmented matrix. So again, this is really messy to keep track of. And if I want to solve this system, I'd first have to reduce it to 2 equations with 2 unknowns, and then I'd have to solve that, and then I've got to go back and figure out what that missing variable ends up being. Instead, I know my 3 variables are x, y, and z, and then I have equals some constant. So what we do is we create a matrix. So we use a square bracket, or you can use parentheses, but it does need to be one of those 2. You don't want to use straight lines because that's going to stand for something else. In the very first row, that is going to correspond to our first equation. The second row corresponds to the second, and the third corresponds to the third. The order you put them in doesn't matter because, again, here, it really doesn't matter which one comes first, second, or third. Okay? Now, that first column is going to be all the coefficients for x. Okay, so if I look at my system, I have 1x. So in the very first spot, I'm going to put 1. Okay, this is called element A11, first row, first column. Then if I look at equation 2, my x coefficient is 2. So I would put a 2 in this spot. This would be corresponding to the second row, first column, because again, it always goes row, column. Then our third equation has negative x, so that coefficient on x is -1. Right? In the next spot, or the next column, we put the y coefficients. Okay? So if I look at my y values, they would be -3, 1, 1 in order. So I put -3, 1, 1. Okay. I have a little bit more room so nothing is squished in here. The next column is then going to be our third variable, which is z. So looking at my coefficients of z, that's 1, -7, and 1. So we put those in that order. Okay. Now what I want to do is I want to make a distinction between my coefficients and my constants. So in place of an equal sign, we're going to put a bar. So that is representing the equal sign. And then in our very last spot, that's going to be the constants. So whatever it equals. So 4, 0, -6. Okay. So this keeps track of everything for us without having to write the variables x, y, and z over and over and over again. It's very clean and very simple looking. Okay. So each row represents an equation and the bar shows you where the equal signs is. The thing you have to be careful about is you do need your system to look exactly like this. You don't want, say, a -4 and equal 0. You need all the constants on one side, the variables on the other. So you should always move the constants to the other side before you write your matrix, okay? Now, if we go through and we could do elimination on this system, that's really going to correspond to what we call these elementary row operations. So it's just going to keep track again of the coefficients. So in the same way we do elimination for solving a system, we can manipulate our matrix using 3 elementary row operations. Very first thing we can do is something I already said. You can always interchange 2 rows. It does not matter which equation you call equation 1, equation 2, equation 3, because from there, you're still going to get the same system. Doesn't matter the order you write it in. Second thing you could do is exactly what we do in elimination. When you want to get them to be the same number but opposite signs, you can always multiply through by a non-zero number. So our second elementary operation is we can multiply a row by a non-zero number. Because if you don't multiply by 0, well, that just wipes the entire thing. And then the third operation is kind of going into elimination. You can always add those 2 equations together to eliminate one variable. So you can add a multiple of one row to another. And that will end up replacing that one row, okay? So we do have a notation to distinguish this as to how to apply the elementary row operations. So we're gonna practice that before we again solve the system. So for this, we're gonna find R3 minus 4R1, then we have this arrow and then R3. Hopefully it's pretty self-explanatory what all of this means. R is standing for row. So this first piece means row 3. Then we're going to subtract 4R1 means 4 times row 1. And then this arrow means this is going to replace whatever row is here. So this notation means we're going to take row 3, subtract 4 times row 1, and that's going to become our new row 3. Now, I will say it can get kind of messy to try to do this in your head. So I'm going to spend the time and actually do all the operations off to the side. It does take a lot more space and it takes a lot of paper, but again, it's very clean because we don't have those variables. And when you get to higher level systems like 5 equations and 5 unknowns, honestly, a matrix is much easier to work with than trying to reduce that system a ton. Your paper would look absolutely nuts trying to get that down to 2 equations and 2 unknowns. So the way I like to go about these is it's kind of like addition or subtraction in this case. I'm going to start by writing what is my row 3. So row 3 is going to be -3, 0, -1. And then I have that bar, so I'm going to replace that here. And then my constant is -5. Then I want -4, row 1. So this is something I can do in my head. I'm just going to multiply every single element here by -4. So 1 times -4 is -4. -2 times -4 gives me +8. And then 1 times -4 is -4. Onto the constant, 3 times -4 gives me -12. Okay. And now this is going to become my new row 3. So I combine these together. So -3 plus -4 is -7. 0 plus 8 is 8. -1 plus -4 is -5. And then I've got my constant, which adds together to be -17. Okay. So again, all this is done is added a multiple of one row to another. So now I get an equivalent matrix that does not change my underlying meaning or solution. My equivalent matrix, the first two rows have stayed exactly the same. We did not touch those, so we copy them. But now I have a new row 3, which is -7, 8, -5, and -17. Okay. So the way we're going to utilize these row operations is we're actually going to get our matrices to a very specific form. And technically there's two different forms that you could get this to. I'm not very particular, especially like in an in-person class, as to what method you end up using, but you do need to be comfortable being able to do these row operations and solve for these systems. So I'm going to show you two different methods. The first does have a specific name. The second just kind of is a simplified version of it, like you don't have to do as much row operations. But our first is called the Gauss-Jordan method, so named after two mathematicians. So the Gauss-Jordan method uses row operations to get our matrices in a specific form, which is called reduced row echelon form. Or you can call it diagonal form. So depending on if you have two equations and two unknowns or three equations and three unknowns, I'll show you what that form looks like. So we'll start with two equations and two unknowns. The idea is you want to get ones on the diagonal and zeros everywhere else. Then what happens to the constants is whatever. The reason this is really nice is because remember, this represents the first variable. This represents the second, equal sign, and then the constant. So if I can put it in this first form, we can immediately pick off what our solution is. The first row tells us we have 1x, and that's equal to whatever the constant is on the right. And then the second row tells us we have no x's and 1y. So you immediately get y is equal to b. And then that corresponds to that point of intersection between the two lines. Or if you have three equations and three unknowns, again, I have no idea what happens over here. They just become numbers. But again, you want ones along the diagonal and zeros everywhere else. Because again, I can immediately pick off our solution. This first equation tells us x with no other variable equals a. The second row tells us y is equal to b. And the third tells us z is equal to c. So again, you immediately get that point of intersection between those three lines, okay? So I'm going to do an example for both a 2x2 system and a 3x3 system. We'll start with a 2x2 system with two equations and two unknowns, just to get in the habit of this. Then we'll jump into three equations and three unknowns, and I'll show you a different method where you don't necessarily have to get zeros everywhere. Okay. So we're going to solve this system using the Gauss-Jordan method. So we've got 3x plus 2y equals -9, 2x minus 5y equals -6. So the very first thing you want to do is you want to write your augmented matrix. So again, I've got two equations and two unknowns. We have that equal sign and then those constants. You can go through and you can pick this off variable by variable. You can also just do it row by row. So we have 3x plus 2y equals -9. We've got 2x minus 5y equals -6, okay? Now, my goal is to get ones here, and then I want zeros everywhere else. So essentially, the process we're gonna follow is you get a 1 in that diagonal position, then you get zeros underneath it. Then you get 1 in the next diagonal position, and you get zeros underneath and below it. And then you keep going through that process. So our second step is you get a 1 in the first diagonal position. And then you get zeros below it. Okay. So I'm gonna go ahead and cheat a little and copy our system. I want to get a 1 in this position to start with. Okay. You could do this a couple ways. Remember, you can also change rows. So if you want to switch that order, you then get a 1 by dividing by 2. But here, to turn this into a 1, I'm going to divide it by 3. So I'm going to take row 1, I'm going to divide it by 3, and that becomes my new row 1. So now I want to rewrite my matrix. We're doing absolutely nothing to the second row, so we leave that alone. And then each of these is divided by 3. So 3 divided by 3 is 1. 2 divided by 3, unfortunately, we do have to leave as a fraction. Then -9 divided by 3 gives me -3, okay? Now I want to get a 0 here. So I'm always going to utilize that 1 I put in the diagonal position because I want to get a 0. So if I take -2 times this row and add it here, that's going to cause a 0. So the operation we're going to do is -2 times row 1 added to row 2 becomes my new row 2. So again, you always utilize that diagonal position to eliminate above and below it. So again, I like to put these off to the side. I'm going to do my operations over here. -2 row 1 plus row 2 becomes my new row 2. And then we need that bar to indicate that equal sign. So if I take this row and I times it by -2, that would give me -2, -4/3, +6. And then we're doing nothing with row 2. So adding these together gives me 0. And then if I do -4/3 minus 5, putting this in thirds is -15/3. So -4/3 gives us -19/3. And then 6 plus -6 gives me a 0. So this creates that equivalent matrix, which we've done nothing in the first row, but now I have a new second row. Okay. Then our third step is, again, I want to put this in a very specific form where I have 1s and then 0s. So I have to turn this next spot into a 1. So we get a 1 in the next diagonal position. and then we get zeros above and below it. So in this case, it is just above because I don't have anything below this number. Okay. So to turn this into a 1, I've got to multiply it by a negative number, and I've got to multiply it by the reciprocal. So we're going to take negative 3 over 19 times that by row 2, and this becomes my new row 2. So again, doing absolutely nothing here. 0 times anything is 0, so those two spots, thankfully, are nice and clean. And then when we times negative 19 over 3 by negative 3 over 19, those cancel each other out, and the minus minus turns positive. Okay. So now I'm looking good. I have 1s in my diagonal positions. Now I want to turn that into a 0. So again, I use that diagonal position to eliminate what's above it. So I want this to be a negative 2/3 so that when I add it together, it cancels out. So we're going to do negative 2/3 times row 2 plus row 1 becomes my new row 1. Okay. And again, this is not going to impact the fact that I put a 1 here because I have 0 below it. So anytime I'm now multiplying this row, it's not going to affect anything in that first column because I had zeros below it, which is the reason we want to go in this very specific order. A 1 in the first diagonal, then a 1 in the second, and then you keep moving on from there. So let's do this off to the side. We're going to take negative 2/3 times row 2. We're going to add that to row 1, and this becomes our new row 1. So row 1, just to put those here, those are untouched. Negative 2/3 times row 2 gives me 0, negative 2/3 and 0. So adding these together gives me 1, 0, and negative 3. So this becomes my new row 1, and then row 2 is the same still. Okay. So now that I have this in that very particular form where I have 1s on the diagonal and 0s everywhere else, our fourth and final step is we turn this back into a system to get the solution. So the first row tells us we have 1x plus 0y equals negative 3. So immediately that tells me the x variable is going to equal negative 3. Row 2 tells us we have no x's, 1y, and that equals 0. So our y coordinate is equal to 0. So this is our solution to the system. Okay. So you could plug it back in. You could check that, yes, this is a point on both of those lines, but it is our solution. Okay. Now, that being said, definitely from the get-go, using elimination or substitution on a system with 2 equations and 2 unknowns is much simpler. This particular process takes a while, but for higher order systems, it's really one of our best methods. So you cannot sit there by hand and use elimination and substitution on 10 equations and 10 unknowns. So a matrix is a much cleaner, simpler way to store the data. And then we can do all these row operations. We also will talk about another method that we're going to build up to doing, and that's involving something called a matrix inverse. But again, we just want to get familiarized with matrices to start, and then we'll show that final thing. So let's try an example now with 3 equations and 3 unknowns, and we want to use matrices to solve that. So this one I'm not going to put in the full reduced row echelon form. I'm going to show you to maybe simplify the amount of row operations you have to do. You can go through this process instead. So same thing again, you immediately start by turning this into an augmented matrix. So I have 3 equations and 3 unknowns. My coefficients from the first one are 1, 1, -1, and 6. And then I put that bar for my equal sign. Second row has coefficients 3, -2, 1, and then a 5. And then we've got 1, 3, -2, and 14. So I'm still going to start with getting a 1 in that first spot, but fantastic, that is a 1, so I don't need to do anything at all. But again, that would be the first step. We get this spot a 1. But awesome, it's done. Then I need to turn what's underneath it into zeros. And I'm going to use that first row to do it. Okay. So if I want to get a 0 here, I need this to be a -3. So I'm going to take -3 times that by row 1, add it to row 2, and that is my new row 2. Okay. So we'll start by doing this operation and we'll update that matrix simultaneously. So -3 times the first row is -3, -3, +3, -18. Then row 2 is 3, -2, 1, 5. So adding these together gives me 0, -5, 4, and -13. Okay. So I'm going to simultaneously update my matrix. First row untouched. And now I have a new second row, which is 0, -5, 4, and -13. And I definitely did not need to make this that big. Don't know why I did. But let's make that a little nicer. There we go. A little bit better. Now I want to get a 0 in this spot. So I'm going to take this times it by -1. So when I add them together, it gives me 0. To give myself a little room, let's go ahead and make those a tiny bit smaller. Now I'm going to take negative row 1, add it to row 3, and this is my new row 3. And then we'll go ahead and put that bar to separate things. So negative row 1 is -1, -1, 1, -6. Row 3 is 1, 3, -2, and 14. So that gives us 0, 2, -1, and 8. So putting that in this spot gives us this matrix. Okay. Now going through, I want to get a 0 here. Well, if I look at that, I would need to divide everything by -5, and that's going to cause some real nasty fractions. So personally, I would rather divide by 2 because -1/2 isn't bad to deal with, and then 8 divides by 2 nicely. So you want to get a 1 in this spot next, but I think it's going to be easier to switch these two, so I just divide by 2 instead. Again, you don't have to, it's just going to be messy fractions that you have to work with. So what I'm gonna do now is I'm gonna swap 2 rows because again, no problem doing that. I definitely don't wanna move this first row though because I have a 1 in the spot I need and I can't change that. So we're gonna swap row 2 and row 3. So the way we say swap is we just do double-sided arrow. So again, gonna cheat a tiny bit. I'm gonna go ahead and swap these 2 rows. So let's just go ahead and delete this. We're gonna swap them, so we'll move out the second row, put that as our new second row, and then our third row goes back. Okay. And again, that's now just a little bit nicer because now we want to get a 1 here. Then if I was doing reduced row echelon, I would need to get zeros above and below. But like I said, I'm going to take a different approach to this one. So I'm just going to get a 0 below it. Okay. So starting out, I want to make that a 1. So we're going to take row 2, we're going to divide it by 2, and it becomes my new row 2. So again, nothing changes in the first row, but now dividing the second row by 2 gives me 1, negative a half, and 4. Now I want to get a 0 here. So in order to do that, again, I use that diagonal element. So I'm going to take 5 times row 2, add it to row 3, and this is my new row 3. So writing that off to the side. Five times row 2 gives me 5, negative 5 halves, and 20. And then we've got 0. Oh, sorry. I didn't write my zeros in my first spot because in my brain I did 0 times 0 gives me 0. Then my row 3 is 0, negative 5, 4, negative 13. So adding those together gives me 0, 0. And then to turn 4, that's 8 over 2 minus 5 over 2 gives me 3 over 2. And then over here, this gives me 7. So I have my updated row 3. Which is 0, 0, 3 halves, and 7. Okay. Now from here, I can actually go ahead and just solve the system. So I, again, don't need to make this a 1 and then turn those into zeros as well. We're going to use a process called back substitution to solve the system. So we start with the bottom row and then we're going to work backwards. So if I look at row 3, what that tells us is we have no x's, no y's. We have 3 halves z is equal to 7. So I can solve for z. We go ahead and multiply by 2. That gives us 3z equals 14. And then dividing by 3 gives us not a pretty fraction, but a value for z. So our z coordinate is equal to 14 over 3. Right? Now that I know z, if I look at this second equation, that just involves y and z. But I know that. So now I utilize row 2, which tells me that y minus 1/2 z must equal 4. But I know what z equals, so I plug that value in, and now I just solve for y. So if we go ahead and multiply these two together, thankfully something nice happens. So 14 divided by 2 is 7. So this becomes y minus 7 over 3 is equal to 4. So my y coordinate is equal to 4 plus 7 over 3. Well, if I want to go ahead and add these, I better turn that into a denominator of 3. So 4 is 12 over 3 plus 7 over 3 gives me my y coordinate. Is again not a pretty fraction, but it is a number. My y coordinate is 19 over 3. So I've used row 3, then I used row 2. I have one variable remaining, which is x. So that's where I go back to this first equation. So row 1 tells us x plus y minus z needs to equal 6. But again, I've already figured out what y and z are, so x is my only unknown. So x plus 19 over 3 minus 14 over 3 must equal 6. And thankfully, those have the same denominator, so 19 over 3 minus 14 over 3 leaves us with 5 over 3. So my x value is 6 minus 5 over 3. And again, I've got to put that with the same denominator, so 6 is the same as 18 over 3 minus 5 over 3. So my x coordinate is 13 over 3. So I have my 3 variables, I have that solution. I don't need to write this next thing, but you can if it wants it as a coordinate pair. My x coordinate is 13 over 3, my y coordinate's 19 over 3, and my z is 14 over 3. Okay, so that is the point of intersection between these 3 lines. So again, you don't have to go through this approach if you don't want to, but I will say it's probably a little bit easier for you than trying to get zeros everywhere in there. Just especially when you have fractions, it doesn't work out so nicely. Unlike this first example, when I was going through, I really didn't have like a ton of fractions to deal with. So going through the full Gauss-Jordan elimination is not bad. Okay. All right, so let's try some more examples of this, because if you remember back to when you were doing these systems of equations, there were other instances that popped up where you had no solutions or you had infinite solutions. So what I want to do is I want to show you how do we see that from a matrix, and then also how do we express our solution here. So we're going to do 2 last examples for those special cases. And again, we're going to use matrices to solve this. So we're going to start with the first one. Again, we're going to work with 3 equations and 3 unknowns to get some practice with it. And we want to solve this system. So first thing I want to do is turn this into a matrix. 3 equations, 3 unknowns. First row is -1, 1, 1, -1. I'll put that bar in for my equal sign. Then we've got -1, 2, -3, -4, 3, -2, -7, 0. So my very first step is I want to turn that first spot into a 1, and I don't want to switch anything around because it already is a 1, just the wrong sign. So we're going to go ahead and negate the first row to replace it. Okay. So that gives me 1, -1, -1, 1, and then everything else stays the same. Now I want to get zeros underneath it, so we're turning these two into zeros. Just to keep up with my work, we're turning this into a 1. Now we're turning these into zeros. Okay. So to make the first spot here a 0, I just need to make this, well, I just really need to add them together because 1 plus -1 gives me 0. So one of my operations is going to be row 1 plus row 2 becomes my new row 2. And then my other operation, I want to get this a 0, so I need to make this a -3. So that would be -3 times row 1 plus row 3 becomes my new row 3. And so this first one will stay completely untouched, but my other two are going to transform. Okay, so starting with this first operation, again, let's go ahead and write these out. Row 1, row 2, and now my new row 2. Row 1 is 1, -1, -1, 1. Row 2 is -1, 2, -3, -4. So adding them together gives me 0, 1, -4, -3. So that becomes our new row 2. Okay. Then with our next one, we need -3 row 1 plus row 2 or row 3 becomes our new row 3. So -3 times the first row would be -3, +3, +3, -3. Row 3 is 3, -2, -7, and 0. So again, just copying it from here. So adding those together gives me 0, 1, -4, -3. Okay. Now this, you might see a problem here. You have exactly the same row in both spots. Okay. So when I go to now get a 0 here, what's going to happen is those are going to cancel each other out. Okay. But following my same process, now we get a 1 in that next diagonal position, but that's already done. And then I want to go ahead and I want to get zeros underneath it. So in order to do that, I've got to take negative row 2, add it to row 3, and this is my new row 3, okay? To show you how we can put it in that reduced row echelon form or start to, let's go ahead and also turn this into zeros. Okay. So this will make a 0 below. And then if I want to turn this into a 0, I just need to go ahead and add those together. So row 2 plus row 1 becomes my new row 1. Okay. So let's start with that one because it's the simpler of the two. Row 2 is 0, 1, -4, -3. Row 1 is 1, -1, -1, 1. So adding those together gives me 1, 0, -5, -2. So we get 1, 0, -5, -2. And then this one hasn't changed. Okay. And again, this is why we use that second row to eliminate above it, because it has not changed that diagonal position. Now going through this one, we want negative row 2 plus row 3 becomes my new row 3. So negative row 2 turns this to -1, or sorry, I keep forgetting my 0 at the beginning. 0, -1, 4, 3. And then row 3 is 0, 1, -4, -3. So adding those together wipes everything out, and you get a row of zeros. Okay. So what actually happens is this last row tells us that 0x plus 0y plus 0z equals 0, which is really just saying 0 equals 0. That is always a true statement. So remember, when you ended up with something that was always true, there are an infinite number of solutions. So this is called a dependent system. So even though there are an infinite number of solutions, it's still not every point that works, because they still have to be points on these lines. Like if I try to plug 0, 0, 0, that is not a point on the line, so it is not a solution of the system. But even if it's a point on one line, it still might not be on all three. There's still just a collection of points that satisfy all of them. It just happens to be an infinite amount of points. So we have a really specific way that we need to actually express these. There's going to be one free variable, but the other are going to depend on it. So we express the solution, it's called parametrically. Okay. So one variable is free to be any real number. But the other two variables will depend on that free one. Okay. So the variable we typically let to be 3 is because the third equation would be how to solve for z. That's the one we let to be free. Because now if I go back to these top two, this gives me y and z, and this one gives me x and z. So I'm going to be able to write x and y in terms of the variable z. Okay. So here we're gonna let Z be a real number. The second row of our reduced system tells us the following. So if I go back up here, 0x, 1y, negative 4z equals negative 3. So that second row tells us y minus 4z equals negative 3. Okay. So I'm going to copy this down here just so you can clearly get that picture of it. But this is our matrix that we're working with. So from here, our y coordinate is then equal to 4z minus 3. Okay. So once I pick a value for z, say z is equal to 5, I now know what y is equal to. It's 4 times 5 minus 3. When I pick z to be 2, again, I just plug it in here. That tells me the y coordinate for my point. Then I look at the first row. The first row tells us x minus 5z equals negative 2. If I had not gone back and changed this, I would have had that coefficient for y, and all I would have had to do is plug that value in to get everything in terms of z. So say this was a 1 here, that would be x plus y minus 5z equals negative 2. You just replace your y by 4z minus 3 to get everything in terms of z. But since I did make my life easier and just involved x and z, our x coordinate is equal to 5z minus 2. So now once I pick z to be a number, I now can plug that into each of these expressions to see what my x coordinate and y coordinate have to be. So the way we write our actual solution is it's x, y, z. So my first coordinate is 5z minus 2. My second is 4z minus 3. And my third is that free one. It is just z. And then z is free to be any real number. So the shorthand notation we have that is this notation. This means z is an element of the real numbers. So that's all that this says. So this is our way we express the solution. This tells me what every intersection point is. Because again, I can't feasibly write all of them out because z could be a half, z can be negative pi, it can be positive pi, it can be 5 pi, it can be any number. It's impossible to write every single point of intersection, okay? So again, a dependent system is going to happen when you hit a row of zeros because that is telling you 0 equals 0. We're going to try one more, which is going to be where we have no solution. And so instead of getting 0 equals 0, you end up with something that is false. So let's go through and try to solve this one. So first thing I'm going to do is immediately turn it into matrix form, and thankfully it is just 2 equations and 2 unknowns. So our first row is 2, negative 4, and 6. And then that second row is 4, negative 8, and 5. So hopefully by looking at this, you can tell there's no solutions because you just multiply those coefficients by 2, but you don't do the same thing to that constant. So really these two lines run parallel to each other, but will never intersect. So first thing I want to do is I want to get a 1 in that diagonal position. So we need to turn this into a 1. So I just take row 1, I divide it by 2, and that's my new row 1. So that gives me 1, negative 2, 3. Then I want to get zeros below it. And so in this case, I'm going to have to take -4 row 1, add that to row 2, and that becomes my new row 2. So going ahead and writing this out. -4 row 1 is -4, +8, -12. Then we've got 4, -8, and 5. So that gives us 0, 0, and -7. So when I try to turn that into a 0, it ends up getting rid of both variables, but not the constant. So if you think about what this last row tells us, nothing is equal to -7, and that doesn't work. So the last row tells us 0 is equal to -7, so there's no solution. That does not make any sense at all. Nothing is going to work. The other way you can represent this, remember, is with the empty set, which is a 0 with a slash through it. Nothing is going to be a solution. When this happens, it's not a dependent system. This is called an inconsistent system. Okay. All right, so that is our introduction to matrices. From here, we're going to learn more properties. We're going to do more systems of equations, and we're eventually going to build to the main concept of linear algebra, which is going to be inverses of matrices.